Welcome back. This is the second lecture of first week of our course. In this lecture, we will discuss about discrete probability distribution. In the last lecture, I have left with a particular problem to solve, where I have shown the population distribution of blood group O, A, B and AB, and how much abundant they are in a population. So, we have percentage of each of those. I can represent this percentage also as a fraction. For example, I can write this 37% is nothing but 0.37. Similarly, I can write the other one 2.23, 0.32 and 0.08, and the summation of all these will be equal to 1, because remember these frequencies and proportions, so their summation should be 1. Now, I can represent the same thing also as a histogram, right? I have the frequency in the vertical axis and those blood groups O, A, AB are in the horizontal axis. So, this is the frequency distribution or frequency histogram for this blood group. So, what we are showing here by this data or the histogram is the frequency distribution of blood groups in our population. Now, similarly, suppose X is a random variable and it can take some discrete 6 values 0, 1, 2, 3, 4, 5, right. And somehow we know the probability that what is the probability that X will be equal to 1, probability of X equal to 0, something like that, and those are all listed here. As these are probability, and if you remember, summation of all these probabilities should be equal to 1, right. So, the summation will be equal to 1. Now, I can represent this probability distribution, this probability values also as a histogram, right, just like we did for frequency histogram of the blood group. So, this can look like this. So, this third one is this value is 0.35, right. So, largest point, highest frequency. Now, suppose I do not know these values, I do not have this figure either. I want you to give me a mathematical function which will tell me what will be the probability that X will be equal to 3 or X will be equal to 5. So, I want a mathematical function, and that mathematical function is called probability distribution. So, probability distribution is a mathematical function that will give us the probability of a specific value a random variable takes, right. Now, you must be wondering, this is a data analysis course and why we are talking about random variables, probability distributions. So, let me explain it bit. Suppose you are measuring the OD of a DNA solution. So, what you will do? You will take the DNA sample solution in a cuvette, shine with a light, and then you will measure the OD. And suppose the OD you have got is 0.23. This is the OD you have got, suppose, right. Is this the correct measure of OD, optical density of this sample? Not really, because we have to remember that every machine, every instrument that we use to measure something has some sort of noise. So, what we are getting is not the exact result, not the exact OD, that is the real OD. So, what we are getting? We are getting something like this. We are getting the measured OD that I am measuring and reporting is nothing but summation of the real OD, which I do not know, and is random noise. So, a random noise get added when I make a measurement in any instrument. So, why do I call this noise random? Because first of all, I am quite uncertain about its value. I do not know it, most of the time do not know the origin of it, and I cannot control it. So, we may assume some sort of distribution, again probability distribution for this noise, considering noise as a random variable, but we are quite uncertain about its specific value. For example, suppose the right value of this, the real value of the OD for this particular sample is 0.22, suppose, although we do not know, suppose we assume that this is the value. Then, when I make a measurement, suppose in the first measurement the random noise was 0.01, then that get added to my real value, and what I get reported by the machine is 0.23. I repeat this experiment again. Now, again, although the real OD should remain same, this value should remain same because I am using the same sample, I am just repeating the experiment, but the noise value should change because it is a random variable. So, now suppose I have got a noise of minus 0.02. So then my reported value, my measured value becomes 0.20. You can see this changing, right. So what I am measuring is changing, although the real value of the OD, the measured thing, is constant, but the noise is varying, and it is varying randomly. So I suppose repeated it 2 more times. So I have 4 data, and that is what you do in experiment in reality in lab, right. So you measure 3 times, 4 times, 5 times for the same sample, and then what you do, you take these measurement and report the mean, right. You calculate the average of these, and sometime you may also add the error term, which may be the standard deviation you have calculated from this data. So you can see here that my optical density is actually a random variable. The measured optical density is a random variable because it includes a random noise coming out of my measurement process. So all measurements that we do in science are actually, everything that we measure can be considered as a random variable, and that is why we have to understand their probability distribution. Now in this case, if OD is a random variable, you can easily see OD can take any value bigger than 0, right. 0, it can be 0.1, it can be 1.2, so it is a continuous variable, right. But there are some random variable which are discrete, and in this lecture we will discuss about the probability distribution of those discrete random variable. Now I have listed a few of the discrete random variables. Check the last one. Here, suppose what you are doing, most of the biologists must be doing it regularly in lab. Suppose I have some mammalian cell culture, I have made a cell suspension in such a way that if I take 100 microliter of the cell suspension, and then if I dispense it in a single OL of a 96 OL plate, I will get roughly suppose 20 cells, right. Now if I have 5 OLs, and if I dispense 100 microliter one after another from the same sample, right, do you expect that in every OL you will get exactly 20 cells? No. Our common sense is no. In some cell it may be 20, in some OL it may be 25, in some other OL it may be 19, 10, even it can be 0 also, because there are the way we have diluted, we have only 20 cells in 100 microliter. So you can see here the number of cells that you are seeding in this 96 OL plate is a random variable, and this is a discrete random variable, because cell number cannot be 12.35, it can be either 12 or 13, right. So this is a example of discrete random variable, and there are many of them, and we want to study the probability distribution, some of the commonest probability distribution that we know and very frequently use in data analysis, that we will discuss in this lecture. So let us start with the first most common discrete probability distribution. Suppose I have a coin and I have tossed it. How many times I have tossed it? I have tossed it 4 times. So if I have tossed it 4 times, and then if I ask you to the question that what is the probability of having 2 heads out of these 4 coin tosses. So I will represent it symbolically like this. I want you to calculate probability of H equal to 2. Now to answer this question, the first thing I have to do is to calculate how many ways I can get 2 heads out of 4 coin toss. So let us check that. I have listed the ways by which I can actually get 2 heads out of 4 coin tosses. Those are 6. H, HTT, HT, HT, these are sequence of coin toss, right. So I have 6 of them here. You can explicitly write them the way I have written here, or you can use the concept of combinatorics, and from that you can say, okay, the number of way I can get 2 heads out of 4 coin tosses would be 4 choose 2, which is equal to factorial 4 divided by factorial 2 divided by factorial of 4 minus 2, that is also 2. So what is factorial 4? Factorial 4 is nothing but 4 into 3 into 2 into 1, right. All factorials, so get it by multiplying this number sequentially up to 1, right. So this is equal to 6. So 6 way I can get 2 heads out of 4 coin tosses. Now remember, these are all mutually exclusive event, right. These are all mutually exclusive event, because if you have got this HHTT, you cannot get the other one. And also If you remember, we have discussed about independent events in the previous lecture. Each of these coin toss is independent, because what will happen in my second coin toss is not decided by what has happened in my first coin toss. So, let me use the idea of independent event to calculate the probability of this one, HHTT. So, probability of getting head is suppose PH, then the first one will be PH, the second one is also probability of head multiplied by probability of getting tail into multiplied or probability of tail. So, I have used the product rule that we have discussed in the last lecture. In this way, I can get the probability of each of these 6 mutually exclusive events, where in all cases I have 2 heads out of 4 coin toss. So, that is what it will look like. I have written them in a reduced form. So, the first one is PH square into PT square also, because 4 minus 2 is again square. So, now what is the total probability that if I toss the coin 4 times, I will get the head 2 times. Now, these are all mutually exclusive event, right, and in either of this way I will get 2 heads out of 4 coin tosses. So, now I will use the addition rule that again we discussed in the last lecture. So, I will add this all probability, and that will give me 6 PH square into probability of T to the power 4 minus 2, which is again 2. So, what is this 6? Where this 6 coming from? Because I have 6 mutually exclusive event, and it can be also said it is 4C2. So, now let me generalize this. Rather than saying 4, 2, something like that, let us consider like this. I have done n coin tosses. Probability of getting head is P. So, the probability of getting tail is 1 minus P, because summation of these 2 probabilities will be equal to 1. And I want to know what is the probability that I will get k number of heads out of these n coin tosses, right. So, that will be using, if I use the way we have calculated, the method that we have used earlier for specific value, that 2 heads out of 4 coin toss, I will get, it will be equal to, this probability will be equal to n choose k into p to the power k into 1 minus p to the power n minus k. You can easily identify the similarity what we just derived one slide back. So, in the earlier example, n was 4, k was 2, and this p was we were writing as probability of head, and this one is nothing but probability of tail. So, let us move further. Rather than just keeping ourselves bounded by coin toss, let us make it generalized. So, suppose if I have n independent trials, and in each trial there are 2 mutually exclusive outcome. Either you will get a head or a tail, either you will get a 0 or 1, either it is true or false, success, failure, either it is mutated, not mutated, either the cell died or the cell is not died, something like that. If I have this type of problem and I have done n independent trials, and then suppose the probability of success, probability of death, probability of getting head, probability of getting 1, something like that is equal to p, then suppose x is a random variable and that represent total number of success in n trials, right. So, x is a discrete random number. So, the probability that x will take a particular value k will be equal to n choose k p to the power k into 1 minus p to the power n minus k. So, I have generalized what we have learned from our coin toss problem. In our coin toss problem also we had the same relationship. Here also we have the same one, because coin toss is exactly the same problem. I have n independent trial. In each case I have 2 possible mutually exclusive outcome, and a probability of success, that is probability of head, is given to me. Then the probability that x will take a particular discrete value is equal to n choose k p to the power k into 1 minus p to the power n minus k. This is called the PMF of binomial distribution. What is PMF? PMF is probability mass function. This equation is probability mass function of binomial distribution, which is very frequently used in many calculations. Now remember, this gives me the probability of taking a particular value by this particular random number x. Now coin toss has two options, right? I will get head or tail, or if you are studying mutation, either it is mutated or not mutated, but always it will not be like that, right? So there are some other cases also. But before I go into those other cases, let me represent this PMA, probability mass function, graphically. So what I have done, I have taken a specific value of n and a specific value of p, and then I plotted a diagram. So it looks like this. So for n equal to 10 and p equal to 0.3, that is probability of success, that is probability of head or something like that, is 0.3. Then for each k, I have calculated the probability using the relationship, the PMF that we have discussed just now for binomial distribution, and it looks like this graph. This looks like a bell curve, right? Inverted curve. It looks like what you commonly say normal or Gaussian, but remember, this is not that. This is the probability mass function, PMF, of binomial distribution, and in this case k is discrete value. So the random variable that we are dealing with is a discrete variable. Now let us move into the next most commonly used discrete probability distribution, that is multinomial distribution. What is that? Suppose I have n independent trial, and in this case each trial does not have two outcomes, it has more than two outcomes, and suppose I represent that by k, k mutually exclusive outcomes, and each of these has a associated probability pi. So p1, p2, something like that. For example, if you take the die, right, if this die, each face has a probability to appear if I throw, right. So those probabilities are this p, and summation of all this probability must be equal to 1. Now if I throw this die, suppose 4 times, right, and I ask, tell me what will the probability that I will get 1 times, phase 2 0 times, phase 3 0 time, and phase 4 2 time, phase 5 1 time, and phase 6 0 time. I have thrown the dice 4 times, so obviously I will not get all the phases, right. So I am asking you that, okay, I have thrown it 4 times and I want to know the probability of getting 1 coming up once, 4 coming up twice, and 5 coming up once. 2, 3 and 6 does not appear in these 4 throws. So I want to calculate the probability of that. So if I have to calculate the probability of that, I have to use something called the PMF of multinomial distribution, and it looks almost similar to the binomial one, but only in this case I have multiple other terms because number of outcomes is more than 2. So the probability of a particular event, that is particular type result that you have got out of 4 or 5 or 6 or n number of dice throw, right, n number of trial, is equal to factorial n divided by factorial of x1, that is the one outcomes, that is factorial number of times that has appeared, that is factorial, factorial of x2, factorial of xk, into p1, which is the probability of getting the first phase, for example in case of die throw, right, the first outcome, to the power x1, that is the number of time that outcome has happened, into p2 to the power x2, that is the number of time, x2 is the number of times that particular outcome, second outcome has happened, up to the product up to pk to the power xk. So this is the PMF of multinomial distribution, probability mass function of multinomial distribution. Now let us move into the third and one of the very common on discrete probability distribution that we deal usually in data analysis. That is called Poisson distribution. What is that? Before I go into it, let us take an example. Suppose I am doing DNA sequencing, some method, we will not go into that, some method you are doing DNA sequencing, and suppose obviously any method will have some sort of error in that, mistakes in that. So, suppose the probability or the frequency of error, suppose let me look out, write something, frequency of error in my DNA sequencing, maybe suppose something like lambda number of times, right, per base, right, and suppose that is very low, suppose that is something like 10 to the power minus 4 or minus 5 something per base, suppose, right. So, that means on an average if I sequence 10 to the power 4 bases, I will get 1 error. So, that is my frequency of error. And suppose I have taken a DNA sequence of length L, that is the length of the DNA, right, length of my sample DNA sequence, DNA, and I have sequenced it. So, now I want you to calculate the probability that if I sequence this DNA of this length L, which is very big, L is very big suppose, right, and what is the probability that there will be 3 errors. I do not bother about where the errors are, somewhere in this length L the errors are there. What is the probability that 3 errors will come? Now, remember number of errors are discrete random variable, right, it can be 0, 1, 2 something up to the length L most possibly, right. So, it is not a continuous variable, you cannot have an error of 2.3. So, I want you to calculate the probability that 3 errors will appear in this length L, where lambda is the frequency of error, which is a very small value, and length of the DNA is L, which is a big value. To answer this question, we have to use the probability mass function of Poisson distribution, and Poisson distribution is a special case of binomial distribution, where the probability of success is very low and number of trial is very big. Just like this one, the error frequency of error is low, but the length of the DNA is much big. So, what is Poisson distribution? Let us look into that. In Poisson distribution, we are dealing with a random event that occurs independently, repeatedly with a fixed rate. That rate is fixed, and we have a parameter, we call it mu. Mu is the average number of occurrence of that event in a particular interval of time or space. What do I mean by space? Space could be length, for example, in case the example that I discussed just now, length of the DNA is the space. It can be volume, suppose you are measuring something, number of cells in a particular volume that you have media that you have dispensed, right. So, that can be volume, or suppose some cases it can be area also. And why are bother about time? Because suppose we are trying to calculate the probability of some death of bacteria in presence of a particular antibiotic. So, in that case we can imagine each of the bacteria die with independently with a fixed rate of death, and mu is the average number of death in a particular time interval. So, what I have a parameter mu, which is average number of occurrence of that random event in an interval of time or space, and then x is a random variable for this particular distribution. X is the number of occurrence of the event in that interval of time or space, and obviously x is bigger or equal to 0. So, now Poisson distribution PMF give me the PMF, the probability that x will take a particular value k, and that is given by this relationship, mu to the power k divided by factorial k into e to the power minus mu. So, this is called the PMF of Poisson distribution. So, now let me draw this PMF. This PMF is for PMF for Poisson distribution. So, just like I have drawn the PMF for binomial distribution, let me draw the PMF for Poisson distribution. And here it is. I have taken a particular value for mu equal to 5, and then again I have plotted each value, each probability of 0, probability of 1, probability of 2 using the PMF Poisson distribution. And you can see that this histogram looks just like that of binomial distribution. Again, this is a bell shaped curve, but remember this is not normal distribution, right? This is Poisson distribution, and the diagram is for the PMF of Poisson distribution. So, with this we will end our lecture today. In this lecture we have learned about 3 probability distribution, which are very common discrete probability distribution. So, what we have learned here is that every measurement that we do, every data that we collect is a random variable, and a random variable can be discrete or continuous. Now, in this lecture we have discussed about binomial, multinomial and Poisson distribution. All these 3 are discrete probability distribution. If your number of outcomes in a trial is 2, then it is actually binomial. If the number of outcomes is bigger than 2, then we have to use the multinomial PMF. And if we are dealing with something where we have some event, random event, a particular random event happening independently, repeatedly with a fixed rate, and we know the average number of times that will happen in a particular interval of time and space, then we can use the Poisson distribution to calculate the probability of a particular number of times that event will happen in that interval. And we have to remember that probability mass function, each of these 3 distributions that we have shown, is nothing but the probability of a discrete random variable taking a specific value. That is all for this video, but before I leave, let me give you a problem to solve. Suppose we are analyzing a DNA sequence, and I have written the recognition site for EQR1, GTT, AAC, and you assume that in a random DNA sequence given to you, all the 4 bases appear with equal frequency. Now, suppose I have given you a random DNA sequence of 10 kb, the length is 10 kb, right? Sorry, it will be kbp, right? So, suppose I have given you a random DNA sequence of 10 kilobase pair, then what will be the probability that this random sequence of 10 kbp does not have any EQR1 site? You have to calculate this probability, and using the concept of PMF of 3 different discrete probability distribution that we have discussed, you should be able to answer this question. So, try this one. Till then, happy learning. Thank you.